So now let's move to the next talk. It's my great pleasure to introduce Professor Sang-Yong Lee. In fact, I have met Professor Sang-Yong Lee many times before in both the United States and Asia. I think very happily surprised to know Professor Lee has joined the Yonsei University. So today, Professor Lee, who has also spent a significant portion of his time in industry before he became a professor, he will share with us his ideas on how to use polymer electrolyte design for semi-solid lithium batteries. So Professor Lee, the floor is yours.
Thank you, Shirley. So hello, everyone. It's my great pleasure to attend this forum and to share my recent works on polymer electrolyte, so which can be potentially used for practically viable semi-solid lithium batteries. Okay, one of the formidable challenges of facing lithium-ion battery is the safety failure, such as cell fire or explosion. So stimulated by this increasing demand for safer lithium batteries, so significant attention has been paid to development of all solid-state batteries. So the main advantages of all solid-state batteries have been deeply explained by Shirley and Linda and the other previous speakers. So more importantly, we are interested in the safety gain from all solid-state batteries. In addition, so because we can use lithium metal anode or the lithium-free anode, so we can expect the improvement in energy density, and also we are highly expected to exploit the bipolar configuration, which can add additional the energy gains in the all solid-state batteries. So far, many people have investigated inorganic electrolytes as a potential candidate for all solid-state batteries. So due to time limit, I'm not going to touch the details on the oxide and sulfide. So as you can see, oxide and sulfides have their pros and cons like this. Okay. So however, I'd like to touch the challenging issues facing all solid-state batteries based on inorganic electrolytes. Firstly, the one challenge comes from the inorganic electrolytes themselves. So although the significant investigations have been conducted, however, still the inorganic electrolytes suffer from many challenges in terms of materials and chemical stability and electrochemical stability, and also. Okay, and talking about the cell fabrication and the electrochemical operation. So as you guys are already aware of, the all solid-state batteries should be fabricated via the different cell fabrication procedures, which are completely different from the currently existing lithium-ion batteries. Okay, and also as several times pointed out in this forum, so to enable the electrochemical activity of all solid-state batteries, we need the highly designed the cell pressure condition and cell temperature conditions. Okay, in addition, so we are still worried about how to resolve the grain boundary resistance and then interfacial instability. So those issues should be resolved to enable practically viable all solid-state batteries. So here my question is, so what is our ultimate goal? So our goal of the all solid-state batteries to achieve safety and energy density. So here our question is, inorganic electrolytes is a sole way to reach this goal. So I'd like to suggest that there may be another route that can lead us to close to the all solid-state batteries. That's the motivation of this work. So we try to find out a more facile and practical route to all solid-state batteries in terms of practical viability. So that's why I'm interested in the polymer electrolytes. So the polymer electrolytes started with the polyethylene oxide, as you can see. So however, the pure polyethylene oxide polymer electrolytes have some problems in the ionic conductivity, the narrow voltage window, and definitely flammability, and the other drawbacks should be reserved. So recently, one review paper have comprehensively overviewed the polymer electrolytes, including gel polymer electrolyte, solid polymer electrolytes, and the others. So from this research overview, I have suggested the following requirements for ideal polymer electrolytes that can be potentially used for practical or solid state batteries. Firstly, in terms of material characteristics, so the ideal polymer or the ideal solid state polymer electrolyte should provide high ionic conductivity, and more importantly, we should be careful about the high cationic transference number. Okay, and also the wide electrochemical stability window should be secured, and also the grain boundary and interfacial resistance should be reserved. And more importantly, so the main reason we are interested in all solid state batteries, the safety. So therefore, the ideal polymer electrolyte should exhibit non-flammability and also non-volatility to ensure thermal stability. Okay, and then when we consider the commercialization of all solid state batteries, we should be careful about fabrication and operation of the fuel cell. So definitely one advantage of coming from the all solid state battery is bipolar configuration, and also to enable practical the fabrication and operation. So hopefully the mild temperature and pressure condition should be highly preferred. So based on this understanding, let me show you our recent works. So we have suggested a new class of printed polymeric electrolytes. So here is the more details. So here, please will take a look at this schematic. So in the background, we have chosen non-flammable organic electrolyte. Okay, and then to enable the structural integrity, we have employed the UV cured polymer network, the colored represented by the yellow line. Okay, and also in addition, we have we have incorporated the ceramic nanoparticles to control rheological properties and then to ensure the structural integrity. So here, as you can see, the lithium ions are allowed to move through the non-flammable electrolytes like this. Okay, so firstly, let me explain the non-flammable, the organic electrolytes. So we are familiar with the carbonate-based liquid electrolytes like this. So, however, those materials are not flammable. So my attention was given to the different types of organic electrolytes, so which is nitrogen-based one. Okay, so as a representative example, we have chosen sebaconitrate, so which can provide high boiling point, which is higher than 300 degrees C. And also more importantly, the nitrile is non-flammable in comparison to the conventional carbonated one. And also it can provide the decent ionic conductivity even at room temperature. That's why we have chosen nitrile-based electrolyte as the base electrolyte. Okay, and then let me show you how to fabricate our electrolyte. So we started with the electrolyte paste like this. So electrolyte paste is composed of the sebaconitrate-based organic electrolyte, and then the polymer, the UV curable monomer, and then the alumina was used. Okay, and then these electrolyte paste was printed using the stencil printing technique like this, and followed by in situ UV curing. And here the more important one is throughout the whole process, we do not use any processing solvents such as acetone or the NMP and whatever. So eventually we have obtained the solid state electrolyte like this. So to help you better understand, let me show you the video clips. So, okay. So, oh, sorry. So there is some problem with this video clip. So, okay. Anyway, so here the if you try to print out the with the liquid electrolyte, it is impossible. So, however, our approach was based on the toothpaste like the liquid electrolyte, printable electrolyte, which can be squeezable. So we have successfully fabricated the leather-shaped electrolyte and followed by UV curing. Unfortunately, due to the technical problem, so the video clip wasn't working. Okay, anyway, so here is the underlying so technology enabling this achievement is the the liquid electrolyte is based on the low viscosity, and they show the Newtonian fluid behavior. By comparison, our electrolyte shows a shear thinning behavior, and then more importantly, if you look at the viscoelastic properties at a certain point of shear stress, the G prime and G double prime was crossed over, so which can show this is the traditional thixotrophic fluid behavior. So by exploiting this unique behavior, so we have successfully fabricated the printable electrolyte. So here, so please bear in mind the viscosity values, so the 750 pools, so which is similar to those of the mustard. Okay, so anyway, so our electrolyte paste seems to be similar to that of the toothpaste. So here is the one interesting example. So here the blue color represents our toothpaste-like electrolyte paste, and then we have fabricated the PDMS mold with maze pattern. And then by using this technology, so we have successfully fabricated the micro-patterned the solid-state electrolyte. Here are the results. So here we can fabricate the well-defined micro-scale the solid-state electrolyte. So therefore, we believe this electrolyte can enable the realization of the micro-scale the power sources. Okay, and then based on this understanding, so we have further extended our concept to fabricate the printed electrode. So here important one is the electrolyte. Electrolyte should be embedded inside the electrode. Okay, so here, so you please take a look at this cartoon. So in addition to active materials, carbon additives, and we have incorporated non-flammable electrolyte like this, which was described previously, and along with the UV cured polymer. So here is the fabrication procedure. So similar to what I have discussed previously, so that we have started with the electrode paste, so which contain the electroactive materials, carbon blacks, and then our electrolyte precursors. Okay, and then those paste were the subject to the printing and followed by in situ UV curing. And then eventually we have obtained the electrolyte embedded the electrode like this. So, to make the conventional, the liquid electrolyte based electrodes, so we should rely on the solvent processing based ones, such as NMP or the others. So in that case, we should be careful about how to remove the processing solvent. By comparison, in our case, we did not use any processing solvent. Okay, just printing followed by UV curing. That's all. So we can fabricate electrolyte embedded solid state electrode. So, okay, so when we fabricated the solid state electrode, so including the sulfide or the oxide embedded electrode, so our attention should be paid to how to ensure the bicontinuous ion and electron conduction networks. So that's a very critical challenge we need to overcome. So here we have exploited a new concept such as ionic strength control. So by exploiting this concept, so we can elaborately adjust the dispersion state of the electrode active materials in addition to the carbon blacks. Okay, so and also during the fabrication process, so we needed to be careful about how to control the interconnected the network structure inside the printed electrode. So anyway, so we have obtained the printed cathode and printed anode. As a first trial, we have used lithium carbon dioxide and then lithium titanium as an anode. Okay, so here, so solid state electrolyte was already embedded. Okay, and also again, so let me emphasize again, so we do not use any processing solvent such as NMP. So therefore, you don't have to worry about the drying steps. So we can simplify the fabrication steps of the electrode. Okay, let me skip the video clips. Anyway, so by using this technique, so we have successfully fabricated all printed also semi-solid state batteries. So printed anode, printed electrolyte, and printed cathode. So here are the results. So as a first trial, so unfortunately the thickness of our printable electrolyte was a little bit thicker. However, we now reduced the thickness, which is similar to that of those of the conventional polyolefin separator membranes. Anyway, so this printable electrolyte shows the distant cyclability. Okay, and then the one advantage of all solid state batteries is that we can expect the fabrication in the bipolar configuration. So we have shown this concept. So by using the in-series printing technique, like this, one cell, two cells, three cells are connected in series. Okay, and here are the cross-sectional SEM view. So to demonstrate this in-series connected cell. In addition, so the one interesting benefit of the printing technologies, we can suggest in plane printing. So in plane connected cells can be fabricated, which can provide benefits in the the volume limited the electronic devices. So let me show you one example later. So like this, one cell, two cells, three cells are connected in plane. So here is the result. Okay, as you can see, one cell, two cells, three cells are connected in plane. So by using printing technology, we can make in series and in plane bipolar cell. And throughout the whole process, we did not rely on high pressure and high temperature processing conditions. So here are the electrochemical properties of our cells. As you can expect it, the one cell, two cell, three cells shows the increase in the operating voltage, and then cyclability was stably preserved. And in addition, so no significant difference between in series and in plane cell was observed. Okay, so let me show you the one example that demonstrates the advantage of the in plane configuration. So this work was done in collaboration with the Prof. Park in Yonsei University. And then he is interested in the OLED installed the mobile pressure sensors. So his requirement is he wants to use the batteries with operating voltage 13.5 voltage. So considering this voltage, if we use the conventional cell, definitely which is very bulky. So we have suggest a new concept. So onto the backside of the pressure sensors, we have fabricated Lego-shaped the cells using the in-plane technique like this. So eventually we have obtained a 13.5 solid-state bipolar cell. So we can reduce the volume increase in the resulting the pressure sensors. So here is the operating cell charge and discharge behavior. Okay, so by using cell, so okay, so let me skip the video clips. Anyway, so by using our cells, so these portable OLED installed pressure sensors can deliver electrical signals to mobile phones. Another interesting application is we have combined our cells with the solar cells to address the the charging issues. So here onto the backside of silicon solar cells, so we have introduced our printed cells using the the in-series connection like this. So please take a look at this photo, and then our hybrid cells composed of solar and then our solid state cell was inserted into the credit card. So please take a look at the cross-sectional view. So we can expect from this result that our hybrid cell is very slim. in terms of thickness. And then after exposure to the sunlight for 20 seconds, so that we can successfully operate the LED lamp for longer than the 20 minutes. Okay, and then the normal photocharging and galvanic discharge behavior was observed. And one interesting finding is under the sunlight illumination. So these are hybrid cell can provide. Please take a look at this red line. This is a discharge profile at a discharge current density of 30 C. So with this significantly high current density, no significant drop in voltage thanks to the combination with the solar cell. This is one advantage of a hybrid concept. Okay, so anyway, so this video clip shows the our cell is safe. So it is not exploded after being cut, and also after exposure to flames. So our cell is not exploded. Okay, and then the one potential benefit coming from the all solid batteries. So we can incorporate different types of electrolytes in the anode and cathode side. Okay, for example, talking about the lithium-ion batteries, the cathode and anode is going toward the different direction, the opposite direction in terms of the electrochemical potential window. And also moving on to the lithium sulfur batteries, the operating condition at the sulfur cathode and the lithium metal anode was totally different. However, we are still using the one component based electrolyte. So ideally, the different requirements for anode and cathode are highly needed. So therefore, our goal is to develop electrode customized electrolytes. So however, why it is not impossible? Why it is not very difficult? So this is due to the cell fabrication technology. So in conventional cells, so the anode is fabricated like this, and on top of that, separator, and the cathode, and packaging, and then the liquid electrolyte injected. So with this classical stereotyped cell, so it is impossible to separate the two different electrolytes in one single cell. So here is our result. So we have suggested the printed dual phase electrolyte as a representative example. We have chosen lithium sulfur cell. Okay, so at the sulfur cathode, actually the sulfur cathode prefers the polar solvent to facilitate the dissolution of sulfur. However, this polar solvent is not good for the lithium anode side. So we have separated by using the dual phase electrolyte concept. Okay, so we have chosen EMS as a solvent for cathode and TGDMA for the anode side. The interesting one is the solvent themselves are miscible together. However, when we control the salt concentration, we have separated the two electrolytes like this, which is based on the coordinated electrolyte chemistry. Anyway, using this electrolyte, we have introduced the different types of printed electrolyte like this. So here is more details how to design the dual phase electrolyte based on the coordinated electrolyte chemistry. So here is a very interesting result. So our case is blue line. So our system shows the decent cyclability, which is better than the conventional DOLDMA based electrolyte, and also along with the lithium nitrate additives. Okay, so and then when we use the additives, so after a certain number of cycle number, the shuttle factor starts to grow. So which is limitation of the additive based approach. However, our approach is a kind of the permanent one. Okay, and then no change in the lithium metal surface was observed. Okay, and then the previous speakers, the Professor Hita Kim, introduced the details on the lithium metal batteries. I'm going to skip the details. Anyway, so here our interest is on the send time. Okay, so to increase send time, so we should be careful about the anionic transference number. In other words, cationic transference number. That's why we are interested in the single ion conductor. Okay, conventional liquid electrolytes and typical solid polymer electrolytes are based on dual ion conducting electrolyte. By comparison, the sulfide or oxide, and then the single lithium-ion conductors can provide the cation transference number of unity. Okay, so we can expect the benefits from the single-ion conductors like this. So previous polymeric single-ion conductors were based on the anionic polymers, okay, and then the Lewis acid containing polymers. So which is not which have not fulfilled the requirements of the advanced lithium-ion batteries. So we need different types of approach. So our approach is the cationic polymer-based one. Okay, so we have synthesized the quaternary ammonium-based cationic polymers, which was coupled with the bulky anions, and then when we add the electrolytes containing the lithium salt, so and then here the lithium salt contains the small-sized anions, so then they can exchange the. Okay, so we expect electrostatic cation anion interaction. We control the anion exchange reaction. So eventually we expect this gain. So here, this is our cationic polymers. So our cationic polymers can selectively capture the bulky anions, and the small anions are also. So therefore, the lithium ions are free to move around the cationic polymer-based matrix. So we are interested in the anion trapping effect. Okay, so to enable the high cation transference number. Okay, so the fundamental technology was based on control the anion exchange. So as a lithium salt, we have chosen the lithium FSI, and then as a cationic polymer, so the TFSI anion was attached like this. Okay, so here the FSI anion and the TFSI anion can be exchanged like this. Okay, so therefore, we can selectively capture the FSI anion from lithium salt. So therefore, it can give the freedom for the lithium anion, lithium cations. Okay. In addition to further enhance the anion trapping effect, we have incorporated Lewis acid-based interaction-based the inorganic particles like this. Okay, so here is the more details, and we have designed the cationic polymers enabling anion trapping effect. And in addition, we have incorporated the dielectric nanoparticles based on the Lewis acid-based interaction. And then, as the organic electrolyte, we have chosen non-flammable electrolyte, which is different from the previous one. We have designed the former LiFSI in propylene carbonate, which is also non-flammable, based on the coordinated electrolyte chemistry. So here is more details. So due to time limit, I'm going to skip the details. Anyway, we have carefully the coordination chemistry of these concentrated electrolytes. An interesting one is that our newly designed electrolyte is not flammable. Okay, in comparison to the conventional DOLDMS-based one. Okay, here is the result in terms of anion trapping effect. Okay, as a control sample, so we have used the conventional, the neutral, the polymer network, and then the inactive, the alumina particles. So in that case, we have achieved cation transference number is the 0.4, approximately 1. And then when we replace the inorganic particles with the Lewis-based, Lewis acid-based, containing the inorganic particles, we have improvement in the cation transference number, and then the ion-ion interaction, and then eventually when we combine the Lewis acid-based interaction and ion-ion interaction, so we reach the cation transference number, which is almost the unity, 0.91. Okay, and in addition, we have measured ionic conductivity, no problem, and then the single ion conducting the polymer electrolyte can provide a higher ionic conductivity than the control sample. And then we have measured the NMR chemical NMR peaks to detect the chemical shift, and also from the FTIR measurement, we have demonstrated the FSI anions were captured by cation polymers. Here is the interfacial stability with lithium metal, and then as you expected, so our single ion conductors can provide the benefits in the electrochemical stability window. And then we have measured the descent time. And then as you can see, the substantial improvement was achieved in descent time. by incorporating the single ion conducting capability. Also, we have measured the critical current density, which is 2 times higher than the control sample like this, and the stable the plating and stripping behavior was observed with our single ion conductor. Okay, and then we have measured the interfacial stability with the metal, and then the stable, the plating and the stripping behavior was observed, and EIS profiles verified this profile, and also we have measured the surface change on the cycled lithium metal using the SEM and XPS spectra. So the side reaction was suppressed by incorporating single ion conducting polymer. So the single ion conductor with a high cation transference number played a vital role in enabling stable lithium stripping and plating on lithium metal surface. And then finally, we have fabricated the full cell. So here to increase the energy density, we have used the lithium metal anode. Okay, and then on top of the lithium metal anode, we have printed out our single ion conducting solid state electrolyte, and then we have fabricated our single ion conducting electrolyte embedded the NCM801 cathode like this. Okay, so here, so if you look at the SM image and then EDS image, so our electrolyte was uniformly embedded inside the NCM811 cathode. So here, important one is this cell was fabricated under ambient condition. No high temperature and no high pressure was needed to fabricate this cell. Just printing followed by UV curing is enough. Okay, and then we have investigated electrochemical performance of the lithium metal fuel cell, and then in comparison to control cell, so control cell contains the pristine polymer electrolyte. Okay, so here our single ion conductors. Single ion conducting polymers can provide a higher rate capability, which was verified by the faster diffusion coefficient of lithium, so through over a wide range of the state of charge and the DOD. Okay, and then interesting one is the single ion conducting polymer can provide the improvement in the low temperature performance due to the suppressed polarization effect. Okay, and then in comparison to the control cell, our single ion conductor can provide the superior cycling performance. To understand this better cycling performance, we have examined what is happening in the cathode side. So this result was obtained from the cycled NCM801 cathode. And then as you can see, so for the control cell, so you can find out the side reaction product was formed. However, in our cases, the side reaction was significantly prevented due to our single ion conducting electrolyte, okay, and which was confirmed by the top seams mapping image. Okay, side reaction was significantly eliminated at our cases. Okay, and then as additional evidence, we have examined cross-sectional the FIBSM image. So in the control sample, the particles were disintegrated, structurally disrupted. By comparison, so in our cases, so as you can see, the NCM801 particles can maintain their structural integrity. So that means the single ion conductor so can stabilize interface with the cycled the NCM801 particles. So we can suggest the electrolyte with a high cation transference number enhance electrochemical reliability of NCM801 cathode. This is another noteworthy advantage of using single ion conducting the polymer electrolyte. Okay, and also we have fabricated bipolar cell, and here we have, thanks to the use of the lithium metal fuel cell, we have fabricated 4 stacked cells. So eventually we have obtained the 16.8 voltage. So at this case, this cell can provide a significant improvement in the energy density, specific gravimetric and volumetric energy density. Okay, these values were obtained by excluding the packaging substances. Anyway, so this is one advantage of high energy density obtaining from the bipolar configuration. Okay, and then here is the one significant advantage of our approach. So so let me emphasize again. So our cell can be operated under ambient condition like this. So we have compared our result with the previously reported ones, the sulfide or the oxide-based approaches should rely on high pressure or the high temperature. So by comparison, so our printing-based and the polymer electrolyte-based or semi-solid batteries can be operating under mild condition, so which can be practically viable. So in terms of enabling the commercialization of the semi-solid batteries. Okay, and then so we have further extended our concept to further improve the anion trapping effect. So here we have suggest semi-IPN technology. Okay, so and then here the purple color represents our cationic polymer-based channels, and then the inside of this channel, so the cationic polymers coupled with the bulky anions, and then the conventional the liquid electrolyte was integrated inside this channel. And then the yellow line represents the UV cross-linked the triacrylated polymer network, which was used to act mechanical frameworks. Anyway, so here to achieve solid-state electrolyte, we have incorporated the UV cross-linked ETPTA. And then in terms of electrochemical performance, our attention was paid to the purple region. So through the purple region, we expect anion trapping effect via controlled anion exchange reaction. And also another interesting finding is accelerated lithium-ion transport through the cationic nanochannels. Okay, so here I have already mentioned the anion trapping effect via the controlled anion exchange. So near the cationic polymer walls like this. And then another interesting finding is we have designed the cationic nanoscale channels. So through the nanoscale channels, we expect the lithium-ion transport can be accelerated. Okay, so this is the evidence. Firstly, to enable this approach, we needed to fabricate bicontinuous nanophase separation. Anyway, so I'm going to skip the details. Anyway, here, please look at this schematic. And then this is our cationic polymer structure. And then here the X minus represents a variety of the anionic groups. And then this is the lithium salt. And then, as I explained before, the anions from the lithium salt can be exchanged with the anions coming from the cationic polymers. And the interesting one is the anion size in the cationic polymers is increased from left side to right side, and then so you can find out the increase in the cation transverse number. So that means by controlling the anion size in the cationic polymers, we can adjust the cation transverse number in this single ion conducting polymer. Okay, and then we have focused on the BPH4 anion, which is the most bulk, which is the bulkiest one in the anion groups. And then this is the evidence to demonstrate the anion exchanges. So the PF6 minus was replaced by the captured by the cationic groups, and then the from the animal result, the enhanced dissociation and then increased mobility was achieved. Okay, and then as you can expect, and then the single ion conducting electrolyte shows the stable plating and stripping behavior, and then this is confirmed by the post-mortem analysis. The electrolyte shows the stable and then stable the surface on the lithium metal like this. And then interesting one is the accelerated lithium-ion transport in nanochannels. Okay, so if we measure the ionic conductivity in terms of salt concentration, so up to the 10 to minus 2 more, so those difference between liquid electrolyte and our electrolyte. However, if you further decrease the salt concentration, you can find out the large gap between two electrolytes. So in other words, our electrolyte shows the higher ionic conductivity than the liquid electrolytes. So this was due to the surface charge governed nanofluid transport near cationic nanochannels. Okay, so and then here we have measured the lithium cationic conductivity at room temperature compared to liquid electrolyte, and the activation energy was lower than the control sample. And this is the evidence to demonstrate the benefits of the electrolyte. Our last approach is okay. So let me fasten more fasten, and then is the COF. Okay, so the porous crystalline frameworks represented by the MOF and COF have garnered significant attention. So in our cases, we have designed solvent-free, okay, solvent-free single lithium-ion conducting COF. Okay, so here the anion was covalently tethered into the frameworks, and then no solvent. Okay, and then the only cations are allowed to move through these COF channels. Here is chemical structure we have designed. Okay, and then the pore size is approximately 10 angstrom, and then the ionic conductivity is not so high. However, so this is meaningful without any solvent, and then so we have obtained this value, and then cation transfer number is almost 0.9. Okay, and then the more important one is activation, and is very low. So that means so this framework structure with the directional ionic channels can accelerate ion transport through the channels. So here is the DFT calculation result, and then so between the COF layer is theoretically calculated to be the 3.4 angstrom, which was experimentally verified by the TM image like this. Okay, so therefore we can expect so the COF layers are well aligned in the through thickness direction, and then the stable cycling behavior was observed. Okay, so let me conclude my talk with a brief summary. And then in this talk, so I have demonstrated non-flammable, semi-solid lithium batteries, which can be potentially viable in terms of commercialization. So more importantly, the cell fabrication and electrochemical operation can be achieved under ambient condition. Okay. And then the second part was devoted to the polymeric single lithium-ion conductors. So interesting finding is that these polymeric single-ion conductors can show the stability with the lithium metal anode, and more importantly, with a high nickel cathode. Okay, so which was based on anion trapping effect, and then due to the formation of a nanoscale channel, so we obtained the accelerated lithium-ion transport. Finally, as an alternative to the inorganic ortho sulfide-based one, we have suggested copper-based solid-state electrolyte. So this work was done with the many contributors, and then the finally supported by the NRF in Korea and LG Energy Solution. So thank you for your kind attention.
Thank you, Professor Lee. Thank you very much for sharing with us a large amount of creative work in the lithium batteries. We do have a question for you. In the era of manufacturing of all solid-state batteries, your approach seems to be very interesting. Could you comment on the speed of the UV curing of the printed all solid-state batteries? What kind of manufacturing speed?
It's very important. So I failed to show the video clips. So anyway, so the UV curing was done in less than 30 seconds. Okay, so actually the UV curing time strongly depends on the thickness of electrode and an electrolyte. However, from our understanding, so in most cases less than 1 minute, and hopefully the 30 seconds is enough to fully solidify the components inside the electrolytes and the electrode.
Mm-hmm. So yeah, just to wrap up, so when do you expect this method can be adopted by the EV battery manufacturer?
So yeah, it's my wish, but okay, in comparison to the sulfide or the oxide-based ones, I'd say that this is not completely solid state approach here. However, I believe my approach is in the middle way, so which can give some sufficient time for the sulfide or oxide-based the solid state batteries. So before the commercialization of the sulfide oxide or solid state batteries, my approach can provide a new chance. So we expect before the commercialization of the sulfide oxide based or solid batteries, our approach could be commercially feasible. So hopefully within within 5 years. This is my hope.
Thank you, Professor Lee. Yeah, really glad to hear that. We need some intermediate pathway. Thank you. All right.